So let's pick up again. Notebook. All right, look at example number B. Even without knowing anything about circuit analysis, we should be able to solve with just logic. What's the first thing you see? You have a current. You have a current that's going down here. It gets divided into I1 and I2. Oh, actually, I labeled it I5 and I6. Yeah. You know what? I'll just leave it as it is. Okay. So it's getting divided into two currents. They're both the exact same resistance, 20 and 20. So logic dictates if you have something and you divide it into equal halves, both halves should have the exact same value. A 2 amp current being divided into 20 and 20, 1 amp going down each pathway. It's just a tiny thing, but it is something that you will also encounter in real life. There are sometimes systems that have very symmetrical or that have symmetry. And so you'd be able to verify your answers or verify your system, whether your system is working correctly or not, just by looking at it without any technical knowledge. Okay. And it's not just electrical systems, it could be any system in your own field of engineering. Okay. Now I want to talk about two techniques, voltage division and current division. This will be on the final exam. Okay. If you have not taken a look at the final exam page, I suggest you do so. All the topics that will be assessed are already on there. And so is the exam date. And this is a topic that will be on there for like a couple of points. You know, not like a really big problem, but it'll be a sub question of a larger problem. So voltage division and then in turn current division are both shortcuts. They are shortcuts that allow us to skip one or two steps in circuit analysis. Okay. And they're both derived from Ohm's law. Okay, they're both derived from Ohm's law. Remember, I said on the first week of class and also the last class on Wednesday, previous class on Wednesday, Ohm's law, KCL, KVL. These three are the only ones we need to know because all other techniques that we learn about are based off of these three. So voltage division and current division techniques are shortcuts. They are both derived from Ohm's law. And basically, the principle states, if you have a voltage that is applied to a series connection of resistors, a fraction of that supply voltage appears across each resistor. Okay. And the fraction is given by the value of the resistance. I mean, it's given by the ratio of the value of the resistance to the total equivalent resistance in that circuit. It's quite a mouthful when you outline it in words. The equation is very straightforward. Analytically speaking, if I look at this circuit, I have V1, V2, and V3, right? Current I is flowing through the circuit, is being supplied by the voltage source. I has nowhere else to go except through all the resistors. So in a series circuit, the current always remains the same for all components, whereas the voltage gets divided. Okay, in a series circuit, current remains the same and the voltage gets divided. If we apply KVL, we can write VT, V total, is V1 plus V2 plus V3. Right? Make sense? If you apply Ohm's law, you can write I is VT over REQ, and REQ is R1 plus R2 plus R3. And that's where this derivation comes from. So typically when we talk about these techniques, because it's a non-E major class, we typically do not spend time in deriving every single technique, okay? And here what happens is we can find V1 as a fraction of Vt, and that fraction is given by the resistance, ratio of the resistance to the total equivalent resistance of that circuit, R1 over Req. And that's it. That's the equation. If you have a voltage appearing across a series connection of resistors, you can skip one or two steps and find the voltage across the resistor directly. So V1 is a fraction of Vt. The fraction is given by the ratio of R1 to Req. Similarly, V2 is Vt times R2 over Req. And V3 is Vt times R3 over Req. If you are interested in the derivation, you can send me an email, stop by my office. I'd be happy to go over it. It's just a couple of steps. All right, let's take a 10-second pause. While you write it down, let me know if you have any questions. Any questions at all? Yes. So question being asked is, can we find the total voltage of R1 and R2 by applying the same technique? Am I understanding your question correctly? That is correct. Yes. So question being asked is about combining two or more resistors in a large circuit, and the answer is yes. So there's always multiple ways to solve any problem, whether it's electrical circuit analysis, whether it's mechanical analysis, materials engineering, doesn't matter what field of engineering or science we are in. If you have a system, there's always multiple pathways to find a solution. Some might be more efficient than others. Efficient meaning it might be low cost, it might be lower in terms of time. Sometimes it might be lower in terms of manpower or human power. So it just depends. There is no right or wrong approach. And in this case, the point I'm trying to make is we could find the individual voltage for R1 and R2 first and then add them up because they are in series. If not, we can combine R1 and R2 first and then find the voltage. Does that make sense? Right? We find V1 and V2 and then do V1 plus V2. A series connection of resistors or series connection of voltages will always break down in that polarity that is shown. Okay. So it'll always be plus minus, plus minus, plus minus, and so on and so forth. Okay. So if you apply a voltage that appears across three elements in series, it'll always break down like that. The flip side is if you connect multiple voltages in series, you can add them up. And you have used this every time you might have used a remote control with more than one battery, or any device with more than one battery. As a real life example, if you've used let's say, any remote control, you've inserted batteries in the remote control, you would have inserted something like this: plus, minus, and then minus and plus. Look familiar? And then there would be a stud here, a metal plate. Actually, metal plate is on this side with a stud, and then there'd be a spring for the negative end. And that metal plate is actually connecting the negative end of one battery to the positive end of the next battery. And so the electrical equivalent for this would be, well, this, by the way, is a symbol for a battery. Two horizontal lines of unequal length. The longer line is plus, smaller line is minus. It's basically an example of a DC voltage source. Okay, DC voltage source. So it's plus minus, two voltage sources in series, and the sum of both appears at the other end. It's cheap, it's easy. Well, I wouldn't say cheap. It's inexpensive, and it's easy to implement. Okay. If you've seen Apple's products like Apple mice, which used batteries early on, they had something like this. And many manufacturers use this now. You insert both batteries in the same direction. Aesthetically, it looks slightly more appealing. Okay, they have these nice designs which cover up the springs. I have an example in my, I have one of the old ones in my office. Maybe next class I'll bring it in. But you see the challenge here, right? You have to design an internal circuitry that would take the negative end of this battery and somehow connect it to the positive end here. And internally, you have to take the negative end and go out here. And so that design challenge, amongst other things, is why it costs $100. That's why it's more expensive. But the logic and the electrical system remains the same. You have two voltage sources, and they're both connected in series, and the voltage sources connected in series will add up. You can verify it with KVL, you can verify it with Ohm's law, you can verify that system with multiple different ways. Okay. Anyway, any other questions before we move on to the example? Okay. Homework for the series parallel network. I would say I don't believe I think it should be due on Sunday, but I'll check again on Pearson. So remind me again at the end of class. All right, so let's look at an example very quickly. You have a 15-volt voltage source divided across 4 resistors. R1 and R2 are the same, 1 kilo ohm. The first thing to do is to find total REQ in this series network. REQ as seen by the voltage source VT. In this case, of course, because it's a series connection, REQ as seen from the perspective of the voltage source is R1 plus R2 plus R3 plus R4. 1 kilo ohm plus 1 kilo ohm plus 2 kilo ohm plus 6 kilo ohms. 10:3. And that gives me what? 10 kilo ohms, 10K. REQ is 10K. My equations, of course, V1 is V total times R1 over REQ And so 15 times 1 divided by 10 into 10 raised to 3. Okay, 1 kilo ohm divided by 10 kilo ohms. And so this should give me 1.5. Oh, 1 kilo ohm divided by 10. So this would be just 1 over 10 is fine. Yeah, I don't need to do kilo ohms. 1.5A. 1,000 ohms divided by 10,000 ohms would give you 1 over 10. So I typically have a habit of writing out every equation, no matter how simple it is or how simplistic it is just a good habit to develop as an engineer. That's kind of like stating it as being deliberate and methodical. And so as an engineer, that's a valued quality by corporations. Yes. Yes, volts. Thank you. Volts. And since R1 and R2 are the same, V2 is also the same as V1, which is 1.5 volts. V3 would be VT times R3 or REQ. So 15 into 2 over 10, 5. And so that's 3 volts, which makes sense because R3 is twice as much as R1. So the voltage drop across R3 should be twice as much as V1. Right? So 3 is twice as much as 1.5. All right, 15, 6 are 90. 90 divided by 10 is 9 volts. And that's it. That's the application of voltage division. Yes. Yes, that is correct. Question being asked is, why can we use voltage division? And the answer is yes, that they are in series. Current, of course, remains exactly the same for series connections. There's no other way, there's no other pathway for the current to go, right? So in a series connection, the current is a result of all the resistors working at the same time, the cumulative effect. And so it remains the same value for everything. All right, let's move on to current division. Well, actually, let's give it a few more seconds. The entire procedure makes sense? Okay. One important point to keep in mind, here it shows you a voltage source, but if it's a larger circuit, it may not always be a source. Okay, let's go back one slide so I can use those circuits as an example. Let's see. Okay, here, example C. In example C, what do you have? You have R3 and R4 in series, right? If you find the voltage across these two nodes or between these two nodes, that voltage, let's say it's, I don't know, VR2. That VR2 voltage is the same for R2 as well as R5. Okay. R5 is comprised of R3 and R4. So this is VR2. This is R2, R3, and R4. VR2 is across the series connection of R3 and R4. it's being divided. So instead of finding the current and then finding the voltage across R3 and R4, I can directly apply voltage division and find VR3 and VR4. Okay, so VR2 is divided between R3 and R4. From voltage division, we can write that VR3 is a fraction of VR2, and the fraction is given by R3 divided by REQ of that branch. The REQ of that branch is just R3 plus R4. Okay. Let's take a 10-second pause while you write it down. Think over that and let me know if you have any questions. Does that application make sense? Any questions? Okay. All right. Then let's move to current division. Current division is also exactly the same as voltage division. When you have a current in a circuit, in this case, again, we're just using an example of a source, gets divided into two, I1 and I2. From KCL, of course, we know that I total is equal to I1 plus I2. But the principle is same or similar to voltage division. When you have a current being applied or flowing through a parallel network of resistors, a fraction of that current or current gets divided between parallel networks or parallel circuits, and a fraction of that total current appears through each resistor or through each branch. And that fraction is given by the ratio of the total equivalent resistance of the parallel network divided by the resistor. I1 is a fraction of IT, and that fraction is given by REQ over R1. I2 is a fraction of IT, and IT is REQ over R2. The numerator and the denominator are flipped. Again, it's parallel connection. Voltage remains the same, right? It's the exact same two nodes. The derivation, again, comes from Ohm's law. You find REQ of all the parallel resistors in the circuit. And in this case, it is simply R1 times R2 divided by R1 plus R2. Okay, so the voltage, of course, remains the same. REQ times the current IT. I total gives you the total voltage across both. And then you apply Ohm's law again to determine the current through both branches. Current division only applies to parallel network of resistors. Okay, let's take a pause while you write it down. Let me know if you have any questions. Any questions? Yes. That's the derivation. I can show it to you very quickly. So the question being asked is, how is this equation arrived at? Why is Req in the numerator? Well, if we say total voltage V appears across both, or not across both, across all three branches, I can reduce it, find IT. This is my Req, right? My voltage V is equal to IT times Req, right? And if V is IT times Req, and V appears across R1 and R2, then from that, I can apply Ohm's law again and write I1 is equal to V over R1. And V over R1 is IT times Req over R1. So it allows you to skip that step. Current division allows you to skip those two steps. As I said, voltage division and current division are shortcuts. Okay, they are shortcuts. And those shortcuts are derived from Ohm's law. It's the same derivation for the voltage division also. Does that answer your question? Okay. Yes. Yes. The voltage is the same in parallel circuits. Okay, ready to look at example? Current division, 3 resistors in parallel. Total Req is the reciprocal of the sum of the reciprocals. Oh, 1 over 10. If you have a calculator, please take it out and tell me what the answer is. One over 10 plus 1 over 30 plus 1 over 60. What do you have? 0.15. Anyone seconded, thirded? 0.15. That's more like it. 1 over reciprocal, right? Yes. 6.67. And 6.67 is smaller than 10 ohms, which is the smallest resistor in that network. So more likely than not, that should be correct. Typically, I like to take at least 3 decimal places. So I would take like 6.667 just to get a more accurate answer. But if it's 6.667, then I1 would be equal to I total, or IS in this case, and that would give me Req over R1. So 15 times my Req, which is 6.667, divided by 10 ohms. What is this value? 15 times 6 is 90. 15 times 0.6 is 0.9. So I'm guessing it's 9.999, or probably 10 volts, approximately 10 volts. 2/3 of 15, right? So 1 amp. Oh, not 1 amp. What am I saying? 100, yeah, 100 divided by 10. So 10 amps. 10 amps. And then I2 and I3 similarly would be IS times Req divided by R2. And I3 would be IS times Req divided by R3. those are the equations. But if I wanted to verify my answer, I would look at the resistor values. R3 is 10 times R1. 60 is, sorry, not 10 times, 6 times R1. 60 is 6 times 10. So the current I3 should be 1/6 of I1. So let's say this is I2 and this is I3. R2 is three times as much as R1. So 30 is 3 times 10. So current I2 would be one third of I1. So it'd be 3.333 amps. So if you do the calculation for I2, you should obtain 3.33. Any questions? Does the equation make sense? The method, the steps? Any questions about the methods? And again, as I said, it'll be about a 2 or 3 point question on the final exam. One of each, voltage division and current division. So total of 4 to 6 points. And there are 2 homework assignments that are not 2. Sorry, there's a homework assignment specifically dedicated to voltage and current division. Yes. So the question being asked is how and when should we know whether to use it or not? And that's an important question. If a problem states that use a particular method, then you have to show the answer, the solution using that particular method. Okay. So when I say that I'm going to ask you or assess you on voltage division and current division, the question will state use voltage division to do this. Like in the quiz today, I said apply KVL and determine the voltage, apply KCL and determine the current, right? And the simple reason for that is we are required to teach students certain topics. And then we are required to assess a student's knowledge about those topics. So if I ask you to solve it using KVL, but you solve it using something else, I have no basis for assessment. I don't know whether the student knows KVL or not. I cannot assess it, as simple as that. So I would not be able to give points if you use a different technique. Okay, so it's kind of like a 2-in-1 answer to your question. Okay, then we get into the meat of circuit analysis. Node voltage analysis and mesh current analysis. These are the 2 most important techniques. Again, both of these techniques are built on Ohm's law, KVL, and KCL. Think back to that slide in chapter 1. What is circuit analysis? Circuit analysis is the process of determining the unknown voltages and currents in a circuit. Analytical solutions, right? We want to solve for these voltages and currents mathematically. To do that, we need equations. And to generate these equations, we apply Ohm's law, we apply KVL, we apply KCL. And that's it. That's what we're doing in these 2 techniques. Okay. We are applying KCL, we're applying KVL to generate a bunch of equations, a system of equations, and then we will solve those equations to determine the quantities. So before we do that, I want to talk about node voltages, and I wish to talk about mesh currents. Okay. Node voltages are real. Mesh currents are not. Okay. Mesh currents are hypothetical. They are theoretical. They do not exist in real life. Okay. And this should be R4. This resistor, sorry, not R4, should be R3. The resistor up top between C and D is R3. Okay. So the first thing I mentioned was node voltages are real, mesh currents are not. Okay. Let's take node voltages first. Node voltages indicate you're measuring voltage at a node, right? A node is an electrical junction where two or more components are connected together. In this example, we have four nodes: A, which is the bottom node, B, C, and D. Even if the B and D nodes are not marked like a dot or a circle, it is still a node, right? Different authors, different people like to draw circuit diagrams a little differently. So it might seem a little weird. Like it's instead of being like a solid dot, it's like a circle. That circle is just a junction. It's just a node. That's all it's indicating. Okay. So sometimes in the previous circuit diagrams, you've seen something like this, like a solid dot, right? Solid dot. Still the same thing. It's just a node. Now, if you look at these nodes, we are stating just a single subscript notation: VA, VB, VC, and VD. Right? It's no two subscript notation. And that's because the second subscript is implied. Your baseline is implied. And that's what it means to measure a node voltage. You're measuring voltage at a point with your reference at a predetermined location. At a predetermined location. Remember, chapter 1 said we use two subscript notations, a double subscript notation for voltages. The first subscript is the point of measurement. The second one is the point of reference. If the point of reference, meaning the second subscript notation, is missing, it implies that the reference is automatically predetermined. It's already present in the circuit. In this case, it is node A at the bottom. And that's indicated by the symbol labeled as ground. Okay, so this symbol of three horizontal lines in the shape of a triangle indicate that it's ground or that it is reference. It could also be a triangle like this. Sometimes I've also seen something like this. So it's ground, or more importantly, for our purposes in circuit analysis in 201, you treat it as the reference point, reference node. All measurements in the circuit are with reference to this point. So VB means you're measuring voltage at B with your reference at A. If you are doing this, if you're doing this measurement physically in a lab using a meter, it means you are placing the positive terminal of your meter at B and the negative terminal at A. So VB means VBA. It also means VB0. VB0. Because VA would mean you're measuring voltage at A with your reference at A. You're measuring voltage at the point with the reference at the same point. Then that would mean you obtain 0 volts. Again, important concept. Node voltage means the second point is implied. It's measured with reference to a baseline point. That reference point is known as the reference node. And that reference node could either be given in the circuit, or if you're analyzing the circuit, you can choose whichever point you want as your reference node. And we will talk about that when we get to node voltage analysis. Okay. But most circuits, the reference node is marked with this kind of symbol. Reference node. Make sense to everyone? Let's take a pause. Let me know if you have any questions. Yes, that is correct. So the question being asked is, if we state VB, does it automatically mean VBA in this circuit? And the answer is yes. In this circuit, A is the reference. So if we just write VB, then it's VBA. If we write VC, it means it's VCA. And if it's VD, then it's VDA. Yes. The question being asked is, will the reference always be 0? The answer is yes. Reference node means the voltage at that reference is automatically 0. It's automatically 0 volts, but the important caveat, the important point is only restricted to that particular analysis. So only for that analysis. Okay. So if I'm analyzing a circuit and I choose A as my reference, then VA is 0. Okay. If A is reference, then VA is 0 volts. If B is chosen as reference, then VB is 0 volts. If C is chosen as a reference, then VC is 0 volts. If D is chosen as a reference, then VD is 0 volts. And that begs the question, how can that be possible? Yes. So in this, the question being asked is, let me see if I understand correctly. What makes it 0 for that analysis? Okay. The question being asked is, what makes the reference node 0? Simple answer, and then I'll talk in depth also. Simple answer, of course, is right here. When we say a reference node, we mean that all voltages at a node in a circuit is measured with reference to that node. So if I choose node A as my reference and I measure voltage at node A, both terminals of my meter are exactly at the same point, node A, which means there is no difference in electric potential between those 2 points. Answer would be 0 volts. Now, to the second part of your question, why is it 0 for any node? Well, then the answer would be, think about voltages from, let's say, problem number 1.46 in chapter 1. There was a question, talks about 4 points in a circuit, and I showed that illustration in class. It doesn't matter where my reference is. Let's say A, B, C, and D, right? This is A, B, C, and D. Two-dimensional graph. If D is my reference, I say that is 0 volts. The level C is 1 volt, B is 1 volt, and A is 1 volt above it. If I choose D as my reference, D is 0 volts. And if I measure voltage at A with my reference at D, what is the value? 1, 2, 3, plus 3 volts. Now, and this is if D is a reference. Now, what happens if C is a reference? What is VA now? 2 volts. That doesn't change the position of the nodes. A, B, C, D will still have a voltage difference of 1 volt. That does not change. It is only mathematical analysis where I'm saying VC is 0 volts. So VA is only 2 volts. And more importantly, here VD is 0 volts, but here VD is minus 1 volt. Okay, think on that. Let me know if you have any questions. So mathematically speaking, you can choose any node you want as your reference. All other voltage levels remain exactly the same. That doesn't change. So when you find the resistor voltages, you will obtain the exact same answer. Does that illustration make sense? Okay, you have A, B, C, D, multiple points in a circuit. The difference between those will remain exactly the same as it is. Choosing a reference node randomly is for us humans. We are writing equations to balance it out, right? The circuit doesn't think for itself. The circuit is, you give me a 10 ohm resistor, then the difference between the two is going to be fixed. It's not going to change. I can change my reference to this end, I would get a positive value. If I change my reference to the other end, I would get a negative value. But the difference between two, the electrical potential difference between those 2 points, that remains exactly the same. That doesn't change. And I always like to use it, but it's sometimes not fair to students, but I always say it'll make more sense when we actually do an example. It's hard to just explain in words. Once we go through the process of finding the voltages in a circuit, it'll make more sense. But the principle remains the same. Whether it's VC or whether it's VD as your reference, the difference in potential remains exactly the same. All right, any other questions? Okay, so that's about node voltages. What we're going to do is then, the next step is we describe each resistor voltage in terms of the node voltages. Okay, we describe each resistor voltage in terms of the node voltages. And so I can write V1, that is the voltage across R1. Voltage across R1 is the difference between B and C, right? B and C is the difference between B and C. R1 is connected between B and C. So we have to note which end of R1 is plus and which end is minus. Plus and minus, the polarity is simply indicating which end is higher potential than the other one. That's all it indicates. That's all. So in this case, with reference to C, B is higher because B is plus and C is minus. So R1 is B minus C. Similarly, V2 is across R2. In R2, C is higher than D. So it's VC minus VD. VC minus VD. Okay, VC minus VD. That's what we have. Sorry, not DA. VC minus VA. A is my reference, not D. And then V3 is between C and D. And so V3 is VC minus VD. And that's why you have multiple polarity or multiple signs at the same node. You see that minus, plus, and plus, 3 different signs at the exact same node. They are not with reference to each other. Okay? This minus sign is related to V1. This plus sign is related to V3. And this plus sign is related to V2. And that's how or why you can have 3 different signs at the same node. All it's indicating is that node C is lower than B, but it is higher than A and D. Yes. No, if it's, so the question being asked is if the polarity was flipped, would we use summation? The answer is no. It would always be a subtraction because voltage is a difference between 2 points. So for there to be a difference, one point has to be higher than the other one. And that comes from the assumption of the current direction. That comes in the next step. So I think if I understand your question correctly, you're asking what if you had B, you have C, and you have D, right? Right now, this is plus, this is minus. And if, let's say, this was flipped like this, right? If, let's say, for instance, C and D were flipped, we would state, in this case, because it's V3 here, we would write that V3 is VD minus VC. That's what it would mean. Good question. Okay, so if it's flipped, you would just use the node which is higher. Okay. All right. Other questions? Other questions? And again, we'll talk a lot more about node voltage analysis next class. I want to just talk about mesh currents before we close. So mesh currents, if you, I stated that mesh currents are not real, they're hypothetical. They do not exist in real life. And mesh currents are rather straightforward, not as involved as node voltage analysis. Okay. Think back to the previous class. I stated a mesh is a simple loop that does not contain any other loops inside it. So mesh is easy to identify. A mesh is a simple loop like this one or this one that does not have any other electrical loop inside it. Okay, so this is a mesh, and a mesh current is a clockwise or counterclockwise current that is flowing through that mesh. So in this case, we have IA and IB. And it's an assumption on part of the student or the engineer. Okay, so mesh currents, again, are not real, they're hypothetical. And the reason is, if you look at R2, we have IA coming down and we have IB going up. It is physically impossible to have two currents present in the same circuit at the same time, both going in the opposite direction. Okay, at least in circuit analysis. When we get to semiconductors, it's a little different. There are currents flowing due to majority minority charge carriers. That's a whole different discussion, so we won't talk about that. As far as circuit analysis goes, mesh currents are hypothetical. They are not real because it's physically impossible to have two currents flowing in the same branch in the opposite direction. Current flows because of a difference in potential between 2 points, right? If both points are the exact same potential, no current is going to flow. One point has to be higher than the other in order for current to flow, right? If my right hand is higher than the left hand, current is going to go from high to low. My left hand goes higher, then current is going to go this direction. So if both of them are the same potential, it's not going to work. Just by definition itself, if one point is higher than the other, then the other point cannot be higher than that one. And so mesh currents are hypothetical. They are not real. They are simply assumptions on our part to be able to solve circuit. Okay, so we'll end class here today. I apologize, I went over a minute, 12:01. We'll end class here today, and I will see you all on Monday. I will have another quiz on Monday, debating whether having first class or the second half of class. Do you prefer the first half or the second half? First half. That's what typically what students have told me. They like to have the quiz done at the beginning of class so they don't have to think about, after that. Okay, so pretty much I was leaning 90% towards keeping it at 10-10, and it'll be based on the series parallel analysis technique. Okay, so I will post it shortly after, after I'm done with all my classes today. Okay, so I will bid you all a good weekend. I will see you all on Monday. If you are taking the lab, I will see you in about 10 minutes.